Preparing for AI Agent Architect interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you define an AI agent, and what core components would you include in its architecture? An AI agent is a software system that observes context, reasons about goals, selects actions, and uses tools to produce outcomes. I design agents as bounded control loops: receive state, choose an action, validate it, execute through a typed interface, then update state. The architecture separates policy from tools and business logic, allowing testing and model replacement. I also define stop conditions, fallback behavior, and audit trails so autonomy remains controlled. While answering, explain the perception, reasoning, planning, tool execution, memory, state management, guardrails, and feedback components. Distinguish an agent from a simple chatbot or deterministic workflow. Question 2. How would you decide whether a problem needs an AI agent or a deterministic workflow? I start with task variability and risk. If inputs, decisions, and transitions are predictable, I prefer a deterministic workflow because it is cheaper, faster, and easier to test. I introduce an agent when the system must interpret unstructured requests, select among tools, or adapt its plan. A hybrid design is often strongest. Deterministic code handles permissions and irreversible actions, while the model handles language understanding and bounded decision-making. Make sure to cover task variability, ambiguity, tool selection, reliability requirements, cost, latency, compliance, and observability. Explain why deterministic flows are preferable when business rules are stable and predictable. Question 3. How would you design an agent that plans and executes a multi-step task reliably? The engineering problem is preventing a long task from becoming an opaque chain of guesses. I decompose the goal into explicit steps with inputs, outputs, dependencies, and success criteria. Each action runs through a validated tool contract and creates a checkpoint in durable state. After every step, the agent verifies results and can retry, replan, or escalate. I limit plan depth and require approval before destructive or externally visible operations. In your answer, discuss goal decomposition, plan representation, checkpoints, retries, tool validation, state persistence, replanning, termination criteria, and compensation for partial failures. Question 4. What is tool calling, and how would you make agent tools safe and reliable? Tool calling lets a model request a defined external operation instead of inventing an answer. I expose tools with strict schemas describing arguments, permissions, side effects, and response formats. The execution layer validates inputs, authenticates the user, applies timeouts, and records every invocation. Idempotency keys make retries safe, while sensitive actions require confirmation. I return structured errors so the agent can recover rather than hallucinate success. Be sure to mention typed schemas, input validation, authorization, idempotency, timeouts, retries, result normalization, least privilege, and protection against destructive or ambiguous operations. Question 5. How would you design memory for a production AI agent? I separate memory by purpose. Short-term memory holds the current task and recent messages. Long-term memory stores durable preferences or facts. Episodic memory records prior interactions when they are genuinely useful. Retrieval should be relevance and freshness aware, not an unrestricted transcript dump. I attach provenance, confidence, retention policies, and deletion controls to stored items. The agent should treat memory as untrusted context and verify critical facts before acting. Cover short-term conversational state, long-term user memory, episodic records, semantic retrieval, freshness, privacy, deletion, summarization, and controls preventing irrelevant or unsafe memories from influencing decisions. Question 6. How would you choose between RAG, fine-tuning, and prompting for an agent? I use prompting for instructions, tone, and lightweight behavior changes. I use retrieval when the agent needs current, private, or frequently changing knowledge, because documents can be updated without retraining. I use fine-tuning when I need consistent formatting, domain behavior, or lower prompt overhead across many examples. In practice, I often combine them, fine-tune behavior, retrieve authoritative facts, and use prompts to define the current task and constraints. In your answer, compare knowledge freshness, behavior consistency, data volume, latency, cost, privacy, evaluation effort, and operational complexity. Explain when combining these techniques is appropriate. Question 7. When would you use a single-agent architecture versus a multi-agent architecture? I begin with one agent because a shared context and single control loop are simpler to evaluate and operate. I split into multiple agents when tasks require genuinely different expertise, permissions, models, or independent execution, such as research, coding, and compliance review. Each agent needs a narrow contract and explicit handoff format. Otherwise, coordination adds latency, token cost, and failure modes without improving outcomes, so multi-agent is not automatically more scalable. Discuss task boundaries, coordination overhead, specialization, shared context, failure propagation, debugging, latency, and security. Emphasize that multi-agent designs should solve a measurable complexity problem. Question 8. How would you evaluate an AI agent beyond measuring the quality of its final answer? A final answer can look good even when the agent used unsafe or wasteful steps. I evaluate task completion, tool selection accuracy, argument correctness, groundedness, policy compliance, latency, and cost. For complex tasks, I inspect trajectories and intermediate state, not just text. I maintain curated scenario tests, adversarial cases, and production samples, then combine automated graders with human review. Every prompt, model, and tool change should trigger regression evaluation. Make sure to cover task success, tool selection accuracy, trajectory quality, groundedness, safety, latency, cost, robustness, human ratings, regression datasets, and online monitoring. Question 9. How would you defend an agent against prompt injection and malicious tool use? I assume every retrieved document, web page, email, and user message may contain hostile instructions. System policies remain separate from untrusted content, and tools enforce authorization independently of the model. I restrict available tools by task and identity, validate outputs, sandbox code, and require confirmation for high-impact actions. I also log suspicious behavior and test attacks such as instruction override, data exfiltration, tool spoofing, and indirect prompt injection. Discuss trusted versus untrusted instructions, content isolation, tool permissions, output validation, confirmation gates, data access controls, sandboxing, monitoring, and adversarial testing. Question 10. How would you design authorization and access control for an enterprise AI agent? The agent must never become an authorization boundary. I propagate the authenticated user, tenant, and purpose through every service call, then enforce permissions at the resource layer. Tools receive scoped, short-lived credentials rather than broad secrets. For sensitive operations, policy engines and approval workflows make the decision outside the model. I maintain immutable audit records showing who requested an action, what context was used, which policy allowed it, and what changed. Cover identity propagation, tenant isolation, least privilege, resource-level authorization, delegated access, approval workflows, secrets management, auditability, and preventing the model from becoming a privilege bypass. Question 11. How would you reduce latency and cost in a tool using AI agent? I optimize the complete task, not just model inference. I route simple classification or extraction to smaller models, cache stable retrieval and tool results, summarize old context, and execute independent tools in parallel. I stream user visible progress while background work continues. Explicit token and step budgets prevent runaway loops. Finally, I measure cost and latency per successful task, because a cheaper response that fails more often may be operationally expensive. Be sure to mention model routing, prompt and result compression, caching, parallel tool calls, bounded planning, token budgets, streaming, batching, and measuring cost per successful task. Question 12. How should an agent handle errors, retries, and partial completion? I classify failures before retrying. Transient network errors may use bounded exponential backoff, while validation or authorization errors require correction or escalation. Every side-affecting tool supports idempotency, and durable checkpoints prevent repeating completed work. If a later step fails, the agent either runs a defined compensation action or reports partial completion clearly. Circuit breakers protect dependencies, and the system stops rather than improvising when recovery could create financial, legal, or safety risk. In your answer, discuss typed errors, retry classification, exponential backoff, idempotency, checkpoints, compensation, circuit breakers, user communication, and escalation when recovery is unsafe. Question 13. How would you design human-in-the-loop controls for an autonomous agent? Human review should be risk-based, not attached to every step. I allow autonomous low-impact actions, but pause before irreversible changes, external commitments, sensitive disclosures, or unusual spending. The approval screen explains the proposed action, evidence, parameters, and consequences, with options to edit or reject. I use reversible operations where possible and define timeout behavior explicitly. Measuring override rates helps tune thresholds without creating constant approval fatigue. Discuss risk-based approval thresholds, preview and confirmation, escalation triggers, reversible actions, user context, timeout behavior, audit trails, and avoiding approval fatigue. Question 14. What observability would you build for an AI agent in production? I instrument an agent as a distributed workflow. A trace links the user request, model calls, retrieved sources, tool arguments, state transitions, approvals, latency, token usage, and errors. Sensitive prompts and outputs are redacted or access controlled, while hashes and metadata preserve debugging value. Dashboards track success rate, unsafe attempts, retries, cost, and dependency health. Sampling and retention policies balance diagnosis with privacy, compliance, and storage cost. Cover distributed traces, prompts and responses with redaction, tool calls, state transitions, token usage, latency, failure reasons, policy events, correlation IDs, and privacy-aware retention. Question 15. How would you prevent hallucinations in an agent that answers from enterprise data? I reduce hallucinations by constraining the agent's evidence, not merely telling it to be accurate. Retrieval applies tenant and document permissions, returns authoritative passages with freshness metadata, and requires citations for factual claims. The agent must abstain when evidence is missing or conflicting. For critical workflows, a verifier checks claims against sources or systems of record. I also evaluate unsupported answer rates, citation correctness, and calibration rather than relying on subjective fluency. Mention authoritative retrieval, citation requirements, access filtered search, grounding checks, abstention, freshness, structured tool results, confidence calibration, and verification of high-impact claims. Question 16. How would you manage state and concurrency when many agent tasks run simultaneously? Each task receives a durable identifier and an isolated state record containing goals, events, tool results, and current status. I prefer append-only events with version checks, so concurrent workers cannot silently override decisions. Leases or queues coordinate ownership, while idempotency handles duplicate delivery. Cancellation and timeouts are first-class states. User, tenant, and task boundaries prevent context leakage, and ordering rules determine which events may safely update shared resources. Be sure to cover durable state, optimistic concurrency, event sourcing, task identifiers, leases, distributed locks, idempotency, ordering, cancellation, and isolation between users or tenants. Question 17. How would you select and route models for different agent tasks? Model routing should follow measured task requirements. I use smaller, faster models for classification, extraction, and simple tool selection, reserving stronger models for ambiguous planning or synthesis. The router considers context size, required structured output reliability, privacy constraints, latency targets, and cost. I define fallbacks for rate limits or quality failures and monitor performance by task type. Routing decisions should come from evaluation data, not model branding or assumptions. Discuss capability, reasoning depth, context length, structured output reliability, latency, cost, privacy, fallback models, confidence signals, and evaluation-driven routing rather than intuition. Question 18. How would you enforce reliable structured outputs from an LLM-based agent? For machine-consumed decisions, free-form text is an unsafe interface. I define versioned JSON schemas with required fields, enums, bounds, and explicit null behavior, then use constrained decoding or function calling where available. A validator checks both syntax and business semantics. Limited repair may be attempted, but repeated malformed output triggers a fallback or escalation. The schema is treated like an API contract, with compatibility tests and telemetry across versions. Cover schemas, constrained decoding, function calling, validation, enum restrictions, repair limits, semantic checks, versioning, and safe handling of malformed or incomplete responses. Question 19. How would you deploy and scale an AI agent platform for production workloads? I separate the control plane from execution workers. An API accepts requests, durable queues schedule tasks, and stateless workers run agent steps against persistent state. A model gateway centralizes routing, quotas, retries, and provider failover. Autoscaling considers queue depth and token throughput, while backpressure protects dependencies. I version prompts, tools, policies, and models independently, use canary releases, and degrade gracefully to search, manual handling, or a simpler workflow. In your answer, address stateless workers, durable queues, model gateways, autoscaling, rate limits, backpressure, regional deployment, secrets, versioning, canary releases, and graceful degradation. Question 20. How would you architect an AI support agent that can investigate issues, update systems, and escalate safely? I would build a bounded support workflow rather than an unrestricted operator. The agent authenticates the customer, classifies intent, retrieves permitted account data, and uses read-only diagnostic tools first. It can draft a fix, but production changes require policy checks and explicit approval. Every response cites evidence and records actions. If confidence is low or risk is high, it hands off with a concise timeline, gathered facts, and recommended next steps. Cover intent classification, identity verification, retrieval, diagnostic tools, ticketing integration, permission boundaries, approval for changes, evidence-based responses, handoff context, and success metrics. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.